Now it's time to talk about electric circuits. So what are circuits? An electrical circuit is a set of electrical components connected in such a way that they provide one or more complete paths for the movement of charges. So they're just a pathway that charges can move through. So for instance, if you have a string of Christmas lights plugged into an electrical outlet, the bulbs, the electrical outlet, the wires all form an electric circuit. And this is a closed pathway for electrons to follow. Electric charge are electrons. I'm sorry, I forgot to pull that up for you. And these pictures also show you that. Now look real quickly because we're going to look at something in just a moment, or actually we'll do it with our next slide. Now, if there is a complete pathway, that equals a closed circuit. For instance, look at the picture on the right at the bottom. The one with the arrows around it is a closed circuit, and the light bulb is lit up, if you can notice that. I'm not sure if the picture is clear for you or not. But do you see how there's no breaks in the circuit? So it's a closed circuit, so electrons can constantly travel through that pathway and light up the light bulb. Look at the light bulb that's closer to the middle. Do you see how the wire is detached from the battery source? That means the circuit is broken, so it's an open circuit, and there's not a complete pathway. So therefore, if you don't have a complete pathway, you have an open circuit. Now, switches actually have something to do with circuits as well, and they can interrupt the flow of charges in a circuit. That's what you do with the light switches in your house. When you open the switch, you're turning off the lights because what it's doing is it's breaking that circuit where no flow of charges can happen. When you close a switch, you're turning the lights on, and that's where you're closing the switch so it allows the pathway to be complete and the flow of charges can resume. And you can see that in the picture on the left-hand side at the bottom. See how the switch is open? So the circuit's broken and you cannot have a flow of charges. Now, if you look to the picture on your right, you can actually see the switches when they're closed. And it's showing you that it has a complete circuit that they can travel. Now, a schematic diagram is a graphical representation of a circuit that uses lines to represent wires and different symbols to represent components. So basically, it's just a lot of lines and symbols that we use to draw what a circuit would look like. And schematic diagrams use standard symbols. Now, if you'll look on the back of your notes, because I didn't have anywhere on the front, on the back of your notes I've actually put a picture of the standard symbols that we normally use. And some of them you'll see here, and some of ours, like I don't use the circle and the X for the light bulb. I actually usually use a little drawing for light bulb, but the battery is the same, the switch is the same. We use lines to represent the wires. We'll use a little squiggly line or a zigzag to represent resistors. Now let's talk, there are actually two types of circuits that we have. We have series circuits and we have parallel circuits. Let's go ahead and talk about series circuits. These are electrical devices, electrical devices can be connected as a series circuit, and a series circuit actually allows the voltage to be divided among the different electrical devices that are there. And a series circuit have a single path for current. If you look at the picture at the bottom, there is just one pathway that the current can flow. And if one element along the path in a series circuit is removed, the circuit will not work. Like if you remove one of the resistors in the picture below, the circuit is broken and it's then opened and it will not allow electricity to flow through it. Now, it's very important we're going to have to learn the difference between series and parallel, and you'll need to be able to draw these series and parallel. So just be aware of that. Now, parallel circuits. These are devices that can also be connected as a parallel circuit, which we've talked about, so that the voltage is the same across each device. So if you had 3 light bulbs, they wouldn't have to share voltage in this instance. They could actually have the same voltage. Now, parallel circuits have multiple paths for current. As you can see in the picture below, it actually has 3 branches. You have the first branch at R1, The second branch, as you can see, R2, and the third branch, R3. Now that's telling you resistors, but that's just so that you know that there are 3 branches in this parallel circuit. And as you can see, there are 3 different pathways that the electrons can follow. If you break any one path in a parallel circuit, it does not interrupt the flow of charges for the electric charge in the other pathways. So let's pretend, like right here, this resistor, we took it out, or it had blown, like maybe it was, it had broken. The pathways for branches 2 and 3 can still be running. It's just the branch 1 that would be out of commission. Now, electrical energy and electric power. Let's talk about that just for a moment. When a charge moves in a circuit, so when it's traveling through those circuits we just saw, the charge actually loses energy. And some of the energy is transformed into useful work, such as the turning of a motor, but some is also just lost as heat. So when we say loses energy, remember, we're never going to lose it that it's destroyed. It just transforms into something else. So it either transforms into useful work or into heat. Now the rate or the speed at which electrical energy is changed to other forms of energy is called electric power. And we can actually calculate electric power, and power is usually measured in watts. And to calculate power, we actually just say current times voltage. So P equals I times V, because remember I equals current. Current is measured in amps, but in the formula it's represented by I. Now I want you to pause the video, go ahead and draw your circle so you have it ready. And then I would also like you to go ahead and do practice problems 1 and 2. Once you've completed practice problems 1 and 2, resume the video to check your answers. Now, as you see, number 1, the power was 500,000 watts. Number 2, the power was 71.92 watts. If you got these correct, you can go ahead and fast forward the video through my examples. If you did not get them correct, hang with me. I know it'll take a little bit longer, but I'll show you actually how you were supposed to do them, and let's see if you can figure out where you went wrong. Make sure you write down any questions you have, as always, so that we can answer them in class. Okay, let's look at number 1. It says a generator at a power plant produces electricity with a voltage of 2.5 times 10 to the 4th volts and a current of 20 amps. How much power does the generator produce? So power is what we're looking for. It gave us voltage, which is 2.5 times 10 to the 4th, and then it gave us current, which was 20 amps. So all we do is we figure out our formula, P equals I times V, and then we plug in the numbers, 2.5 times 10 to the 4th times 20.0. And what you get, once you multiply that, is 500,000 watts. Let's go ahead and look at number 2. A refrigerator uses a current of 0.62 amps and a voltage of 116 volts. How much power does the refrigerator use? So we've got current is 0.62 amps, voltage is 116 volts, and it asks how much power. So we have power equals I times V again, and we plug in our numbers, 0.62 amps times 116 volts. And our power, once you calculate that, is 71.92 watts. And please write down any questions you have or circle the area that you did wrong if you're not sure you understood it, if it doesn't look like the process that I did. Now let's finish up by talking about fuses and circuit breakers. In electrical devices, the overall resistance, remember resistance slows down the charge, the overall resistance is lowered and the wire carries more current than it sometimes needs to, and the circuit can then be overloaded. So the high currents in overloaded circuits can cause fires, and that's a danger. That's a lot of reason why houses burn sometimes, while we have, again, the Christmas tree fires. Fuses and circuit breakers can actually reduce this danger, okay? So And I'm sorry, I keep forgetting to press my arrows. So we use fuses and circuit breakers to help reduce the danger in house fires and things like that. Even car fires, there are fuses in cars, and we'll talk about that more at school. Now, when two wires touch, like an example of the picture at the left, they create an alternate pathway for current, and that actually creates a short circuit. Okay. Now, fuses, I'm going to talk about how fuses work, and then we're going to talk about how circuit breakers work. Fuses melt to prevent circuit overloads. Because a fuse is an electrical device that contains a little bitty metal strip that melts when current in the circuit becomes too great. So an example is like a fuse is like a ribbon of wire that has a very low melting point. And when we say that a fuse blows out, we're talking about that what happened was the current exceeded the level that that fuse could endure. So when the current in the circuit reaches a certain level, the fuse will blow out. Now an example, a 20 amp fuse will melt if the current in the circuit exceeds 20 amps. And that way it shuts everything down because it's taking on too much current. And that's actually how it helps and reduces the danger for us. Now let's talk about how circuit breakers work. Circuit breakers open up circuits with high current. So just like we saw that switches will open up a circuit, that's what the circuit breaker does. They are made up of switches that open up a circuit so that the current can no longer flow once it gets too high. And so the circuit breaker is a switch that opens a circuit automatically when the current exceeds a certain value. Now certain circuit breakers use a magnet or a bimetallic strip that responds to current overload. Okay, so it's made a little bit different. And unlike fuses, circuit breakers can be reset by turning the switch. Okay, for your summary, this is what I'd like you to explain. I would like you to explain the flow of electrons in a simple circuit and a parallel circuit. Tell me the differences between those and the differences between the electron flow. I hope you have a great evening, and I'll see you in class.